history of generation and water releases, but how does one predict flow changes considering the wide range of hydrological and market conditions that can be expected? A first step is to combine temporal differences in the costs of purchasing replacement electricity with the availability of water or hydropower to meet contract demand. If the cost of replacement electricity was the same as the cost of hydropower, we would expect suppliers to be indifferent about how power is provided to meet contract demand. Also, if there are no temporal differences in the cost of replacement energy, there could be no savings to store water overnight and releasing it during the day. Fortunately, the power engineering literature provides a firm foundation to predict how thermal and hydropower plants would be dispatched to meet load. Dispatching thermal power plants is pretty straightforward since operational characteristics are similar and not subject to stochastic variation in weather. We built our discussion around Wood and Wallenberg, a graduate-level power engineering text entitled Power Generation, Operation, and Control. Hydropower is different from thermal power plants. Not only is each reservoir and dam uniquely different, every dam has different environmental constraints. The Wood and Wallenberg text develops power dispatching rules for all thermal power plants as a group, coal, natural gas, and nuclear, and hydropower is a separate case which requires special consideration. However, the literature stops short of incorporating complex environmental constraints. Wood and Wallenberg have developed a dynamic programming solution to the integration of thermal and hydropower generation resources. Their approach, like ours, involves finding the minimum cost trajectory to meet contract demand. This approach is cost minimization via the Lagrangian method, equating the marginal value products of generation resources. We have extended the Wood and Wallenberg method to incorporate dynamic head effects. The faster water is drawn down in the reservoir, the lower the productivity of the water release. We also have incorporated hourly release constraints to restrict the flow fluctuations we pointed out at Glen Canyon. We really want to focus on the complex constraints affecting the diurnal flow shape because this is the major source of concern about hydropower operations. It is also mathematically difficult and hasn't been done before. Once the optimum conditions for dispatching the hydropower facilities were derived, the model can be used to predict hourly and seasonal flow shapes, although the discussion focuses on the hourly changes. We are going to show what the hourly constraints at Flaming Gorge look like using the 3D data block. This time the data block is 24 hours wide and only 7 days long. We have shown 4 sets of constraints to make 4 separate points. First, a minimum flow of 400 cubic feet per second is shown in the foreground. A minimum flow of 800 CFS is shown in the second block. In both instances, minimum flows are floor values that cannot be violated. The third data block shows a range of possible flows assuming generation peaks once a day. The fourth data block assumes generation could peak twice a day. In both instances, we assume the maximum allowable change is 1000 CFS per hour. You might remember in the Glen Canyon example that flows were peaking twice a day. This orthogonal view of the constraints gives a little better perspective on the constraint shape. The constraints are repeated for 7 days to reinforce the idea that constraints are assumed to remain the same over the simulation period. The structure of the model is conceptually pretty simple, even if the solution gets complicated. Inputs to the model are demand, which is another way of describing customer load, market prices for replacement energy, the cost of producing electricity from hydro sources, hydrology or the amount of water available to produce hydropower, and reservoir levels which allow us to calibrate hydropower production as reservoir head rises and falls. The model permits the user to change any of these input values according to scenarios of interest, and inputs could be generated stochastically to incorporate uncertainties about the market or weather. The environmental constraints incorporated in the model are also user changeable. The constraints govern minimum flow, hourly release rates, and the total amount of water that has to be released during the period. Other constraints, including seasonal constraints or constraints on reservoir levels, could be incorporated as long as they are specified beforehand. Recall that to minimize the cost of meeting contractual commitments, water is likely to be released during the day when demand is high and replacement power purchased from the market is relatively expensive. Because generation is equivalent to downstream flow, with some adjustments for productivity factors like head effects and attenuation, we've now identified how hydropower marketing is linked to downstream environmental impacts, as long as we identify the flow constraints and market conditions in the service area. We have created another 3D data block to show the predicted pattern of releases at Flaming Gorge under the constraints identified above and representative market conditions. This data block is 48 hours wide and 30 days long to show a month of hourly hydro generation values and the amount of power purchased on the market to meet contract demand. For each hour of each day, generation is shown on the left and purchases on the right. The data object is shown for two simulation cases which represent two different sets of environmental constraints. A baseline case, which more or less reflects constraints on historical operations, and a low max case, which limits generation to about 75% of generation potential. This top view shows the baseline case at the bottom and the low max case at the top. Generation is shown on the left and purchases on the right. From a side view, note that under the baseline case, purchases are made during two distinct periods during the day, unlike the low max case. This pattern is driven by the environmental constraints. Notice the shoulders on the low max data block, whereas the baseline case is more angular and block shaped. This top view of Flaming Gorge generation data shows the familiar pattern of high releases during the day and low releases at night. Generation is shown on the right this time. The low max case is in the foreground, and each day of the 30-day period is virtually the same, with a small increase in generation from day to day revealed during the noon hour. Keeping the low max case in the foreground, note the highly uniform releases predicted by the model. The historical releases we showed for Glen Canyon were not so uniform, but the pattern of diurnal shaping was apparent. The diurnal pattern is also apparent at Flaming Gorge, and we have some historical generation data from the third quarter of 1995 to illustrate it. This view has been reversed to offer a better perspective of the hydro shifting event. AM is on the right and PM on the left, with the end of the third quarter in the foreground looking towards the beginning of the period at the top of your screen. Moving a little closer, the shape is easier to see. Notice the one observation sticking way up by itself on the left-hand side of your screen? This is actually a transcription error of the raw data, which was left in the picture to show how quickly the eye can identify abnormal values with this visualization technique. The half-pipe shape in blue is the hydroshifting event predicted by the model, although in this case we are actually looking at historical generation, not model results. Why doesn't the historical data match the model prediction? Sometimes market conditions do not warrant hydroshifting, cost differentials are small, and sometimes there isn't enough water to shift into on-peak periods. The first quarter of 1989 at Flaming Gorge is a good example of low operational flexibility in a dry year. Remember the data block showing constraints for minimum flow? During the first quarter of 1989, generation at Flaming Gorge was nearly constant at minimum flow for the entire 90 days. What little extra water was available during the first quarter has been moved into the on-peak period during the day. Wet weather can also mean low operational flexibility. 1983 was a wet year across the Colorado region. In this case, there is so much water to be released during the month, the generators at Flaming Gorge were loaded to maximum capacity for most of the period. The few instances where flows drop below maximum generator capacity usually happen at night. The diurnal pattern is repeated, but not so extreme as might be observed during an average year. During 1983, the dam was nearly breached. No wonder flows remained so high for so long. Notice the holes in the middle of the data block. One wonders whether system maintenance was scheduled or the units were taken offline for a short while due to some emergency. To summarize some of our findings, we observe fewer hydroshifting events when weather is very dry or very wet, regardless of the environmental constraints. We also observe fewer hydroshifting events when the cost of purchase power is low, that is, being close to the cost of producing hydropower. By making a few assumptions, the cost of environmental restrictions can be determined. Hydropower operations costs increase about 40% from the baseline to the most restricted baseload case. following clip is a short video taped from an interactive manipulation of the Glen Canyon 1983 dataset. The clip shows how datasets can be examined to explore relationships among the data elements and to determine regions of the dataset that are of particular interest.